Welcome to an exploration of how nanomaterials behave completely differently from bulk materials due to their enormous surface area. At the nanoscale, materials have an enormous surface-to-volume ratio, with most atoms sitting on the surface rather than in the bulk interior. Let's start by understanding what surface-to-volume ratio actually means and why it matters. For any spherical particle, the surface area grows with the square of the radius, while volume grows with the cube of the radius. Surface area equals 4 pi r squared. Volume equals 4/3 pi r cubed. The surface-to-volume ratio is therefore 3 divided by r. Notice how it's inversely proportional to radius. Here are 3 particles at different scales. As we shrink the particle, the surface-to-volume ratio increases dramatically. Let's work through a concrete example using a gold nanoparticle to see real numbers. Consider a gold nanoparticle with a 10 nanometer diameter, which means a 5 nanometer radius. The radius is 5 nanometers, or 5 times 10 to the negative 9 meters. The surface-to-volume ratio is 600 million per meter. That's enormous compared to bulk materials. Now let's compare this to a macroscopic gold sphere with 1 millimeter radius. The surface-to-volume ratio is only 3,000 per meter. The nanoparticle has 200,000 times more surface area per volume. An important question is, what fraction of atoms actually sit on the surface? Let's calculate how many of the total atoms are actually surface atoms in our gold nanoparticle. In a nanoparticle, red surface atoms outnumber blue interior atoms. Most atoms are touching the outside environment. A gold atom has a radius of about 0.144 nanometers. In our 5 nanometer radius particle, roughly 30 to 40% of all atoms are surface atoms. That's almost half. The surface fraction scales approximately as 3 times the atomic diameter divided by particle radius. Using our numbers, that's about 17%, though the actual value is higher due to atomic packing effects. When particles shrink to just 2 nanometers in radius, more than half of all atoms are sitting on the surface. One dramatic consequence is that nanoparticles melt at much lower temperatures than bulk materials. Let's ask ourselves, why would a tiny gold nanoparticle melt at a lower temperature than a gold bar? In bulk gold, every atom is surrounded by 12 neighbors in a close-packed structure with strong metallic bonds. Surface atoms have fewer neighbors, maybe only 6 or 8 instead of 12. These undercoordinated atoms are less tightly bound. Answer: surface atoms have fewer bonds, making them higher in energy and easier to break free into the liquid state. The melting point depression follows this equation. Delta Tm equals negative 4 sigma times bulk melting temperature times molar volume divided by heat of fusion times radius. Sigma is the surface energy, Vm is molar volume, and delta Hm is the heat of fusion. Gold normally melts at 1337 Kelvin, or about 1064 degrees Celsius. Gold's surface energy is approximately 1.5 joules per square meter. Gold's molar volume is about 10 to the negative 5 cubic meters per mole. The heat of fusion is approximately 12.5 kilojoules per mole. Let's calculate the melting point for our 5 nanometer radius particle. Plugging in the numbers, we get negative 4 times 1.5 times 1337 times 10 to the negative 5, divided by 12.5 times 10 cubed times 5 times 10 to the negative 9. This gives us approximately negative 128 Kelvin depression. So our gold nanoparticle melts around 1209 Kelvin, which is 128 degrees lower than bulk gold. This graph shows how melting point decreases dramatically as particle size decreases. The smallest particles melt hundreds of degrees lower. Another critical thermodynamic property that changes is heat capacity. Heat capacity tells us how much energy we need to add to raise a material's temperature by 1 degree. Heat capacity C equals the derivative of heat with respect to temperature. Let's ask, how does having so much surface area change the heat capacity? In bulk materials, atoms vibrate with strong coupling to their neighbors, giving predictable heat capacity. Surface atoms have weaker bonds and different vibrational modes, storing energy differently than bulk atoms. Answer: surface atoms contribute differently because they have fewer neighbors and different vibration patterns. The nanoparticle heat capacity is a weighted average: surface fraction times surface heat capacity plus bulk fraction times bulk heat capacity. Measurements show gold nanoparticle heat capacity can differ by 10 to 20% from bulk gold. This matters enormously for thermal management in nanoscale electronics and photonic devices. Phase transitions become broader and less sharp in nanoparticles. In bulk materials, transitions like melting happen at one precise temperature with a sharp discontinuity. Bulk materials show a sharp discontinuity at the melting temperature. Energy jumps suddenly as latent heat is absorbed. Nanoparticles show broadened transitions. Melting occurs gradually over a temperature range as different parts of the particle melt at different temperatures. Why does this broadening occur in nanoparticles? Different atomic layers have different melting points. Surface melts first, then inner layers progressively melt. The width of the transition scales inversely with radius. Smaller particles have broader transitions. In very small 3 nanometer particles, melting can be spread over 50 Kelvin instead of being sharp. Surface energy becomes a dominant contribution to total energy at the nanoscale. Total energy equals bulk energy plus surface energy. Bulk energy scales with the number of atoms N times the cohesive energy per atom. Surface energy equals surface area times surface energy density sigma. In macroscopic bulk materials, surface energy is completely negligible compared to bulk energy. But in nanoparticles, surface energy can represent 30 to 50% of the total energy. In macroscopic materials, bulk energy dominates at 95% with only 5% from surface. In nanoparticles, surface and bulk contributions become comparable, each around 50%. This high surface energy makes nanoparticles thermodynamically unstable. They want to minimize surface area. That's why nanoparticles naturally aggregate or sinter together, reducing total surface area to lower energy. The Gibbs-Thomson effect describes how particle curvature affects equilibrium conditions. The chemical potential change equals 2 sigma times molar volume divided by radius. This chemical potential change affects vapor pressure, solubility in solutions, and all phase equilibria. Smaller nanoparticles have higher vapor pressure. They evaporate more easily than larger particles. Vapor pressure equals bulk vapor pressure times exponential of 2 sigma Vm over RRT. Let's calculate this for our 5 nanometer gold particle at 1000 Kelvin. P over P0 equals exponential of 2 times 1.5 times 10 to the negative 5 divided by 5 times 10 to the negative 9 times 8.314 times 1000. This gives about 1.007 or 0.7% higher vapor pressure than bulk gold. For even smaller 2 nanometer particles, vapor pressure increases by about 2%. At the smallest scales, quantum confinement also affects thermodynamic properties. When particles become comparable to electron de Broglie wavelengths, quantum mechanics becomes important. The thermal de Broglie wavelength equals Planck constant divided by momentum, or h over square root of 2 times electron mass times Boltzmann constant times temperature. For electrons at room temperature, this wavelength is approximately 5 nanometers. In bulk materials, electron energy levels form continuous bands. In nanoparticles, quantum confinement creates discrete energy levels instead of continuous bands. The energy level spacing scales as Planck constant squared over 8 times mass times radius squared. These discrete levels dramatically affect heat capacity, especially at low temperatures where only a few levels are populated. Below 100 Kelvin, quantum confinement can change heat capacity by factors of 2 or more compared to classical predictions. These nanoscale thermodynamic effects have major practical implications. In catalysis, surface atoms are where reactions happen. High surface area means more active sites. Reactant molecules approach surface atoms, where catalytic reactions occur with high efficiency. In drug delivery, nanoparticle size affects how quickly drugs dissolve and become available in the body. In electronics, Understanding heat capacity and thermal transport at the nanoscale is critical for managing heat in tiny transistors. Battery electrodes use nanostructured materials to increase surface area for faster charging and higher capacity. Chemical sensors exploit high surface area to detect tiny amounts of target molecules with high sensitivity. Let's summarize the key insights about nanoscale thermodynamics. First, the surface-to-volume ratio scales as 3 divided by radius, becoming enormous at the nanoscale. Second, in particles below 5 nanometers, 30 to 50% of atoms are surface atoms. Third, melting points can drop by 100 Kelvin or more following the Gibbs-Thompson equation. Fourth, heat capacity and phase transitions behave very differently than bulk materials predict. Fifth, surface energy becomes comparable to bulk energy, representing 30 to 50% of total energy. Finally, while these effects enable amazing new technologies, they also create stability and processing challenges. This concludes our exploration of nanoscale thermodynamics and its implications for materials, science, and engineering.